All right, hey, I got a question here, and I'll make a video solution from chapter, what was this, 32, number 18. Let me call this page 1, because I think this math might get kind of long here. But let me just read the question here. It says, the switch in the figure is open for time less than 0, and then is thrown closed at t equals to 0. So maybe I should draw the circuit here. They've got a 10-volt power supply that comes up and goes to, I'll call it the first resistor, 4 ohms. It hits a little node, so the current's going to split. Some of it will go down, I'll call it the central piece here of 4 ohms. Other of it will go to the right-hand side of the circuit, and it goes through an 8 ohm. But it's this 8 ohm that's the interesting new one, because here's where we put this in inductor. And so there is a 1 Henry inductor. Essentially, this branch here, the 8 ohms and the 1 Henry inductor, are then in series with each other, and that's in parallel with the 4 ohms. Oh, and I got to put a switch here, and so there's a switch. And so they say that the switch is closed at time t equals to 0. So if I got to thinking about the current here, before I go through the detailed mathematics, because the question says, find the current in the inductor and the current in the switch. So maybe I'll start thinking about the switch for a moment. When I close this switch, and of course before it was closed, so at time t equal to 0, I would get 0 current. That's pretty obvious. But when you first close it, if you remember an inductor, the voltage on the inductor is this minus L di dt. That means it opposes the change. This is Faraday's law. And so we can think of inductors as creating enough voltage that it will not change the current instantaneously. It'll keep whatever it had the moment before. So in this case, the moment before was no current, so it would keep no current. So right when you close the switch, you could say, okay, well, these are kind of out of the picture. And so we just have current coming out of the 10-volt battery, and it essentially is going through 2 4 ohms in series, which is equivalent to 8 ohms. And 10 divided by 8 is 1 1/4. So what's going to happen is the current's going to pop up real quick to 1.25. Now that's in the switch, because if I do the same kind of thinking for the current as a function of time in the inductor, again, before the switch is closed, it would be 0. But as soon as you close that switch, it's still 0. It doesn't change instantly. Now, of course, the other neat thing that we learned here with the inductors is you only get a voltage because there is a change. So even though when you first close the switch, the current is 0, that doesn't mean it's not in the process of changing. It would be a lot like we did in Physics 121, where you took an object and you dropped it. You said, okay, let's hold it. As soon as you let it go, right here, its motion is 0, so it has no velocity, but it does have an acceleration. It's in the process of changing. So it may have 0 speed when you first let it go, but it has an acceleration, and it's in the process of changing. And so it soon will have a speed. And that's what I'm going to say here with this current. The inductor is going to then build up. And eventually it will build up so that there are no more changes going on. And when that happens, there's no voltage here. Yeah, and so when that happens, we would just kind of ignore that and say that this right here, we would have a 4 in parallel with an 8. So that's going to make an equivalent of 2.66. That equivalent is in series with the 4, so it's 6.66. So 10 divided by 6.66 is 1 1/2. So what's going to ultimately happen is this is going to climb up to 1 1/2 coming out of this battery. And so it's going to build up like that. Now, this is actually a current divider. So this 1 1/2 is going to come out of here and hit this node. And since this has twice as much resistance as this will get most of the current. This will get twice as much as that. So if we break this into three pieces, 2/3 of it will go this way, and 1/3 will go that way. So the 2/3 here would, let's see, the total current was what, 1.5? So 2/3 of that would be 1 amp. So 1 amp's going to be rushing through here, and so the other half amp's going to go through there. So that would answer my long-term current for, half, for my inductor. So the whole current, the current in the switch is going to build up to eventually 1.5 amps. So it quickly jumps up to 1.25, then it grows, and that's what we got to solve for, that equation. And then it gets 1.5, and then, of course, the inductor is doing the growing also, and goes from 0 up to a half an amp. Okay, but that was not really what the question was about. It wasn't really asking to find the immediate current and then the long-term current. But I like to do that at times, and that kind of helps me at least kind of figure out where I should go long-term. The problem we're asked to do is to find the current at any moment in time, whether it be right when the switch is closed, whether it be a long period of time, or somewhere like in this transition zone. And so we'll do better than what I just did. I only found the current short-term and long-term and realized there's got to be some kind of transition, but I didn't really solve for that. So I want to do that. So let's do that. Let's say that the current coming out of the battery is I1. It gets to this node and splits. So let's call the stuff going down number 2 and the stuff going around the right-hand loop number 3. Because what I'm going to then call equation number 1 here would be the node rule. The current's coming in, which is I1, would equal what comes out, which would be I2 plus I3. So notice I'm really going back to chapter 28. This is the Kirchhoff's node rule that simply says, according to conservation of charge, the current coming in, which is I1, has to equal what comes out. So that's 2 and 3. Okay? So there is the first of, and of course I would need 3 equations because, as we talked a lot about in chapter 28, we need 3 equations to solve for 3 unknowns. Okay, so my other 2 equations would be Kirchhoff's loop. So let me do the left-hand loop. This would be what I'll call equation number 2. This would be 10. Then I guess it would be minus 4I1. And coming down here would be another resistance of 4, but a current of I2. That would complete the loop. And so I would get 0. So there's the left-hand loop. Let me do the right-hand loop. Maybe I'll start down at this bottom here and go around clockwise. So I'd go against the current. So that's a plus 4I2 minus 8I3. And then there's the new piece, minus LdIdt. And that would be current 3 equals 0. So there's my 3 equations and 3 unknowns. Now, one of them has a derivative in it. So unlike chapter 28, I'm not going to grab my calculator and say, hey, let's head over to the matrix and solve a system of linear equations. Well, I don't have a system of linear equations. Now, 2 of them are linear equations, but the third one makes it a differential equation. So I really have a set of differential equations. I don't know if I'd call it a whole system. They're not coupled to differential equations, but I guess technically because one of them has a derivative in there, it is a system of differential equations, or at least one of them is. So I'm going to have to solve this by hand. Okay, I'm going to have to restart my video and splice this together. My alarm went off. I have an important meeting soon, but I think I have enough time here to finish this up, and then I'll send it out when I get a chance. Okay, so let me solve this here. And so the first thing I will do is merge 1 and 2 together. And why don't I just rewrite equation number 2, or at least start to write it. And right here where it says current number 1, I will substitute in number 1. So this would be I2 plus I3. And so that goes right there. And then this would be minus 4I2 equals to 0. Now, of course, the nice thing about that is now I have an equation that is the combination of 1 and 2, and it only has the variables I2 and I3. And so the result of this, together with the third equation, which only has 2 and 3, and it gives me 2 equations and 2 unknowns. So that's where I'm headed here. Maybe I'll combine a little things, because distributed, this is a 4I2 and another 4I2. So that makes a total of minus 8I2. Then the distributive law here is a minus 4I3 equals to 0. So that's the equation I get after merging 1 and 2 together. And of course, now you can see where I'm headed, because I need to get rid of the I2. So why don't I merge this equation, which I will call 1 and 2, and let me merge it with number 3. Now, maybe even before I do that, watch this little quick step. I'm going to divide by 2. So this becomes a 5. This becomes a minus 4. I2. This becomes a minus 2. I3 equals a 0. And the reason I decided to divide by 2 is because I'm looking up here at equation number 3, and they have up here not just I2, but it's 4I2. And so this right here is 4I2. And so maybe I'll just do a 5 minus 2I3 and move the 4I2 to the other side. And so what 4I2 is equal to is this right here. And that's kind of nice, because I can then take that and put it into here. Actually, I'll just do an extra space. So finally now, let me merge this one right here, which is 1 and 2, together with 3. And right here, this 4I2, I'm going to put a 5 minus 2I3. Of course, then I'll have the minus 8I3, and then minus the L di3 dt equaling 0. All right. Well, actually, I thought that would need more pages, and we might be able to get this done in 2 pages. Don't want to rush it, although I do have that meeting coming in. That's why that alarm was there. Okay, so let me go ahead and look at this equation. It only has I3s in it. So this would be the 5 minus 10I3 when I combine those two together. And let me move this to the other side. So instead of having a negative, I now have a positive. And I'll even do one step better. This L, if you remember back here, is 1, because it's a 1 Henry inductor. So makes my math a little bit easier if I just put in the number 1 for L. It just becomes di3. All right, so this is obviously the differential equation, and it is separable. I think I mentioned a couple of times here that your author really only gives you any problems that's going to have separable differential equations, because you can solve those real easy. Those are the easiest of all the differential equations. They're still not easy, but they are the easiest. And so what they mean is put everything of the same variable on one side of the equation. And so dividing both sides by 5 minus 10I3 would get rid of this whole thing on this side, and that would just be a 1, and would put then the I3 together with the di3. And then, of course, if we multiply both sides by dt, that would eliminate time on the right-hand side. So on the left-hand side, we have just the I3s. And on the left-hand side, we have just a dt. And that's the big step of solving any of our differential equations, is make it separable. So now we can solve by simply integrating. We don't have really anything complicated to do because we only have one variable. Now in this case, I'd put in my limits, and so they say that go from 0. And so here's a nice little trick if you didn't catch it in past lectures. The limit doesn't have to be a number. I mean, if they ask for the current I3 after say 10 seconds, I would go 0 to 10 seconds. If they ask for 5 seconds, I'd go 0 to 5 seconds. Okay, but if I just said after t seconds, t becomes the variable. And so I'm going to say after t seconds. And what would happen on this side of the equation is I would start with the 0 current. So that's why it was kind of important at the beginning to realize my starting point, my initial at time equal to 0 is 0 current. And then after a little bit later, I don't know what the current is, but I'm going to label it with a symbol, called current number 3. So after I do this integral and put in the limits, this would be at the end of time t, I would have current I3. So then I can put in whatever number I want now that I have an equation. I could put in 10 seconds here, and then that would give me the current after 10 seconds. I could put in 5 seconds, and so this would say if I put in t for 5 seconds, I would have the current after 5 seconds. So this is the easiest integral. This is just t evaluated from 0 to t. This one, of course, takes a little more thinking. We could do a u sub, but I don't think we have to go quite that complicated. We know that a u sub then when integrated would give a natural log of our u sub, so that would be the u sub. But then processing the u sub would have this negative 10 in it. I like to check it by saying I'm going to take a guess and then take its derivative and see if I get back here. So let me take the derivative of this. I take the derivative of this, the negative 10, on just my mind, I'm going to pull it in front, and I would get 1 over that, so that's good. But then the chain rule would give me the negative 10 in the numerator, which is why that one's there to cancel it off, because nothing's supposed to be left. No negative 10 is left after I take the derivative. So that's perfect. And so it's evaluated from 0 to I3. Okay. And so why don't I move the 10 over to here, so that would be negative 10, and then just times t when I put in the limits. This one would be ln of 5 minus 10 I3, and then minus ln of what do I get when I put in 0, and so that would be ln of 5, which is really nice because you use the property of logarithms. You can take a subtraction of 2 of them and write it as a quotient. So now I can finally get rid of the natural log by raising it to a power of 10. Now bringing the 5 over to here. And maybe switching positions, bringing the 10I3 over, and then subtract this over here, the 5e to the minus 10t. And to finally get I3, I might then divide by the 10. And they each have a factor of 1/2. And so there, hopefully, is the current for the inductor. And it does seem to match what I got over here, which was this growing up to 1/2 amp. And so it would start off at 0, and this term would go away, and you eventually end up with a 1/2 amp. So the plot of this would look like that, peaking out at 1/2 amp after a period of time. Okay, so my initial thinking about the inductor did match my math at the end. That's a good sign there. Okay, now the other half of this was to find the current in the whole switch, which is current number 1. And so maybe to do that, I should come back somewhere. Maybe this equation would be the good one to find equation number 2, because this would then be 5 minus 2, and in place of I3, I'll put this equation, 1/2 times 1 minus e to the negative 10t. And so 5 minus 2 times 1/2, blah, blah, blah. Okay, equals 4i2. So you can see that the 1/2 goes away. And so we have a 5. and it looks like a 5, this would be a minus a 1, and then this would be a plus e to the negative 10t is equal to 4i2. And of course, 5 minus 1 is a 4. Looks like I am going to need another page. And let's see, if I bring the 4 over, 4 divided by 4 is 1, plus, and then the 4 divided by here is then a quarter, and then e to the minus 10t is equal to I2. All right, so now going to the first of our series of 3 equations. Where did it go? Right here, where we can get the current in the switch as adding these two together. All right, so this is 1 plus 1 quarter e to the minus 10t. So that's I2. And then I3 was this 1/2 minus 1/2 e to the minus 10t. So that would be I3. I'm sorry, I1. Oh, I got it over here, I1. All right, so the numbers would add together. So this would be a... oops, there was my second alarm. Okay, all right. So I gotta get out of here. I gotta start up my computer here and go to my meeting. But I think we're done here. So where was I when the video camera cut off here? And I got to splice this together. But I put these together, so that's 1.5, and then minus, and so this would be minus 1/2 and plus 1/4. So that's minus 1/4. E to the minus 10, and so that is current number 1. Yay! And I should flip over to the solutions here real quick. Let's see, what does it say? Current number 3. Where did I do current number 3? Right here. And so current number 3, which is the switch, has a 1/2, 1 minus e to the negative 10 it, good. And then the current in the switch, 1.5 minus 1/4 e to the negative, is that a 10? 10t, yay, okay, good. All right, got to run. I'll post this when I can, bye.